Dear students, welcome back. This is Dr. Biju Vasudevan, and here we are going to discuss Calculus 2 Math 112 for week 12. In this video, we will discuss chapter 6.6 work. The next part of the video, probably in a couple of days, we will discuss hyperbolic functions. Okay, let's start with the work 6.6. The definition 6.61 says that if a constant of force of magnitude F is applied in the direction of the motion of an object, if you find an object is here and it's at the position A and there is another position B, you are moving this object in this direction and the force applied on it is F and the distance the object covered is D, then the work done is F dot D. The product of these two constant, because you are given force, the magnitude of the force and the distance D. Okay, what's the problem here in this chapter? Suppose that an object moves in the positive direction along a coordinate line while subjected to a variable force f of x. Now, if the force is not a constant, f is not a constant, it's a function of x, variable force. Then how to find the formula, how to derive the formula, that's what we are going to discuss. That is applied in the direction of the motion. So define what is meant by work W performed by the force on the object as the object moves from A to B. So let's find a formula for this case. Alright. Okay. What's going on? So before going to the formulas, some basic information. There are three possible cases. First, you can get an international system of units SI, in which force can be given as a Newton and meter, distance can be given as meter. If you get force is Newton, distance is meter, the work done will be getting the unit joule. If you are centimeter gram second, if you are using centimeter gram second unit system, isn't it? Centimeter gram second system, then force will be given in dyne, distance will be given in centimeter, therefore work will be denoted as erg. The unit of work will be erg. If it is British engineering system, then force will be given in pound and distance will be given in foot, therefore the work done is 4 pound. Okay, remember these three important systems and then we will derive the formula for variable force. Okay, it's given here, I need to write somewhere. Okay, let me introduce it here in this slide. Isn't it? The force formula has been given here as W is equal to integral A to B f of x ds when you are moving from A to B in the x-axis. The distance d is from A to B and the force is variable, can be any function f of x, isn't it? Now it is area under this curve. The work done is area under the curve. So how we design, just like our similar integration, we divide this interval A to B into n small intervals. Starting, this is x0, this is x1, x2, x3, general we call it xk, and we call the previous one is xk minus 1 and the final one is xn. Assuming that the force is constant in every interval, so that the interval will be very sufficiently small, isn't it? So that the force will be fxk maybe at any point in the small interval f of xk star, isn't it? Any point in this interval force is constant. Throughout this interval force is constant, isn't it? Dividing. And for this interval, what is the work? Work is force f of xk star into del xk. Del xk is the difference here. Del x, we can write del x is the difference the length of this interval, xk minus x. So del x you can write xk minus xk minus 1 del x. Del xk we can denote it del xk. Right, now this is the work done for the small part. So there are n such parts, so we have to, this is wk, so we have to find double the entire work done. This interval is summation k from 1 to n f of xk star del xk, and when n goes to infinity we get this Riemann-Son's our work. That is the formula for integration, a to b f of x dx. This is the formula given here. Alright, so this is the formula. When we get a variable force and the distance is from a to b, then integrate from a to b f of x. That is the work done. And Newton's second law of motion gives the formula for force if you are getting mass and acceleration. Sometimes you get a velocity, you can integrate it, differentiate it to get acceleration, then go ahead with the mass and acceleration to find the force. Okay, let's see one more important rule. Hooke's law. Hooke's law says that under some conditions, a spring, that is, so this is a spring, assume that you have a spring here, its normal length is L, isn't it? Original length. This is stretched up to this distance is x. You are stretching the spring beyond its natural length. The natural length is L. Beyond its natural length, this distance is x. You are stretching the spring beyond its natural length. So when under some conditions, what are those conditions? It's not given to find the k. So if the spring is stretched beyond its natural length, it will pull back. When you release it, it will pull back with a force f of x is equal to k times x. F of x is equal to k times x. X is this distance that you have pulled. You have stretched it, isn't it? So k times x. What is this k? This k is called a spring constant. Spring constant and spring stiffness. This differs from the it depends on actually such factors, that the thickness of the spring and the material used for preparing such a spring. So k is different for different kind of springs. So from this formula we can find the value of k. If you have force applied and the distance you have stretched, then you can find k. For every spring we can use this formula to find spring constant k. And let's remember this information, then let's start the exercise at 6.6. 6.6. Okay, first problem. Only few problems are there in this topic. Variable force f of x is given. Yes, this is the force. Force is y-axis. Position, distance is x-axis, isn't it? Okay. When x is 0, y is 1. So we have to design a formula to get the equation of this function. What is the equation of the straight line? How to find the equation of the straight line? If you have 2 points x0, y0 and another point x1, y1, how to find the equation of the straight line connecting these 2 points? The formula is y is a variable, y minus y1 divided by y0, y1 minus y0, that is x minus x0 divided by x1 minus x0. We can use this formula to find. So here you see this point is x is 0, y is 1. So x0, y0 has been given here. This point x0 is 1, y0, and this point x is 3, y is 4. So x1, y1 has been given here. Use them in this formula, y minus y0. Y0 is 1. y0 is 1 and divided by y1 is 4 and then y0 is 1. On the right side, x minus x0 is 0 divided by 3 minus 0. What you get is 5 y minus 1 over 3 is equal to x over 3. So this gives y minus 1 is equal to x, y is equal to x plus 1. This is the equation of this line. Now we got the force. Okay, force. We have defined the force. We have derived the force. F of x is a variable force which is x plus 1. And the distance is from 0 to 3. So obviously work done is integral 0 to 3 f of x dx. Integral 0 to 3 x plus 1 dx. And now you are expert in integration. Do it. X square plus x from 0 to 3 to x square over 2. So when you substitute 2 here, it is 4 over 0 to 3. 3 over 9 over 2 plus 3. And lower limit is 0, everything is 0. This is 4.5, this is 3. So work done is 7.5. What is it? Joule, erg or pound foot. What is it? This pound and foot. So the answer is in pound foot. 7.5. Okay, let's go for problem number 2. From the textbook, it is problem number 3. So for the variable f of x, variable force. So this in the graph it is shown variable force, isn't it? This is variable force. But see, first for the first 2 units, force is constant, 40 units. From 2 to 5, when x moves from 2 to 5, the force is variable. So we need to find only this part of force later on. So this point is x is 2, y is 40. So x0, y0. At this point, x is 5, y is 0, y is 0, x is 5. So this is x1, y1. Just like the previous rule, we will find. Oh, let's do it later on. Let's read the question properly. What's given? Consider the distance d, for which the work done by the force on the particle when the particle moves from x from 0 to d. D is somewhere else, here or here, anywhere between 0 to 2. D is the distance, isn't it? Either is it between 0 to 2 or 2 to 5. Somewhere D is going to be. But the question is, by the time you reach D, if the D is here or anywhere between 0 and 5, by the time you reach D, you are completing half the force done, half the work done. Actually, the total work done up to here should be found. Then half the work will be done by the time you reach D. That's the point here, isn't it? So we need to roughly identify where the D will be before solving it by just analyzing the graph, isn't it? So how the work done when the particle moves from 0 to 5. So let's find. We should know what is the total work done when it moves from 0 to 5 in this distance. So half the work done will be done when you reach a D. D can be here or here. So the first question is based on assumption. So whether D is more than 2.5 or less than 2.5, 2 is here, 2.5 here. So D should be either above D or below 2.5, above 2.5 or below 2.5. That's our question, first question. By assumption, we have to answer it. And we will answer it. We will solve and find what is exactly the D. You see, actually the work done is the area under the curve. The first, when you reach 2, when the distance reaches 2, the force is constant, 40. So when we reach x is 2, the force is constant for the first interval. So 40 is the force, constant force, and the distance is 2. So you are getting 80, because it's Newton and meter, so it is joule. 80 joule work is done by the time you reach 2. And see, this area is the area in the first part is a rectangle which is more than this triangle. So this area, this work done in this interval might have been more than half of the work that is to be done by this by the time you reach 5, isn't it? So 80 may be more than the half. So as per our assumption, d should be less than 2. D should be less than 2, somewhere here, d. So by the time you reach d, half the work might have done. So first we should find what is the total work, isn't it? So the work in the first part up to 2 is constant force and the distance is 2, so total work is 2. Now let's find the work done in this area. Here we will find a force, a variable force, isn't it? So points are x0. So points here I'm writing, this point is x0 is 2, force is y0 is 2. So x0 y0. At this point x is 5, y is 0. So when you use this one, the same formula that we used in the previous problem, you will identify that y minus 40 divided by 0 minus 40, which is equal to x minus 2 divided by 5 minus 2. So simplify this one to get this equation. When you solve this one, just write the answer, you solve it. 200 minus 40 times x over 3. This is the y. This is the equation of the straight line from 2 to 5 in this direction, isn't it? So f of x, 200 minus 40x divided by 3 in the interval when x starts from 2 and ends at 5. So the work should be found in this part. So total work should be found by adding them. Okay. Now the formula for work done is from work done in the second part. I mean, isn't it? Second work done. This is work 1, which is 80 joule. Second part of the work is 225, and the function is 200 minus 40x divided by 3 into dx. So integrate it. 1 over 3 is constant. This is 200x minus 40x square over 2 from 2 to 5. Use the upper and lower limit, get the answer as 140. Work in the second part is 140. I have calculated it, so I am writing the answer straight away. You just substitute the upper and lower limit, get the answer. So total work, what is the total work? First part is 80, second part is 60, this is 60. Total work is 140. This integration will give you 60 and total work is 140. What is half of the work? Total work from 0 to 5. When you start from 0 and end to 5, total work done in this direction is 140 joule. Half the work is 70 joule. Half the work is 70 joule. Half work is 70 joule. So but see, by the time you reach 2, you have completed 80 joule. So D must be in the first half, in the before 2. Because when you reach 2, the total work done is 80 joule. But half work is 70 joule. So D is the place where we complete exactly half the work. So how to find D now? So integral 0 to D. When you reach D, the total work done is 70 joule. So in this D should be here in the first case, isn't it? First interval. It is force into D. So force is constant, 40 and dx. So when you integrate this one, it is 40x from 0 to D is equal to 70. So simplify this one. What do you get? 40 D is equal to 70 and D is equal to 70 over 40. It is 7 over 4. 1 point something near to 1.75 something, isn't it? Okay, this is our D. D is less than 2. That's the end of this problem. Okay, let's go with the problem number 5. Constant force. The constant force 10 has been given. So force has been given as 10 pound in the positive x direction applied to the particle whose velocity has been given. What is the purpose of velocity? Okay, velocity v has been given. When you integrate velocity, you will find distance, isn't it? So velocity should be a variable velocity. Find by using the same point. This is 0, 0, and it is 5, 4. Find the equation of the line. Equation of the line. That is our velocity. When you integrate velocity, velocity is a positive function. See, we know the formula for distance we have seen in week 4. Check back. Velocity is from A to B. Modulus values integrate absolute value of velocity dt if there is a negative part in this function, isn't it? So here velocity is a function here, a function of t. So let's use the same point 0, 0, 2, 5, 5, isn't it? By using the same formula, how to find a velocity. So this is here by using the same formula, it is v minus 0 divided by 4 minus 0, which is t minus 0 divided by 5 minus 0. What we get is v by 4 is equal to t by 5. That is v, velocity, a function of time, is this is t over 5. 4t over 5. So equation of this line is 4t over 5 using the same formula that we have used in problem 1 and 2. When two endpoints are given, you can find the equation of the straight line, isn't it? So we have to integrate velocity to find distance, and then distance should be multiplied by the constant of force, because as far as the force is constant, the formula for work done is force into distance. Only need to find distance. So integrate this one to find the distance. What is the distance? Distance d is equal to integral t is 0 to 5. V, velocity, is 4t over 5 dt, and of course 4 over 5 is constant. When you integrate t square over 2, when you 0 to 5, so 2 can become 2 over 5, and this will be 25 minus 0, 2 over 5 and 25, you will get 50 by 5. This is 10 foot. 10 foot. Distance is 10 foot and the force is constant, which is 10 pound. Therefore work done is 10 again 10, which is 100 pound foot. That's the end of this problem. Next is spring problem. A spring problem. There are two problems. I discuss them. Yes, we will solve it here. There are two problems in the board actually. Okay, we don't have space to solve. We will solve here. Problem 6. The force given here is a constant force 6. When it is stretched, when the spring is stretched, see, spring is here, and your this is original length is natural length is 4 meter, and from here to here you are stretching 4.5. This is half meter. You are stretching extra, isn't it? So when it is stretched from the spring exerts a force 6n. The force here is 6 Newton and the distance is meter. And we know by Hooke's law, we know force is k times x. This is 6 is equal to k times half. So what is k? That's the question here. K is 12. We have found a spring constant. We will use this to find the second part of this question. So find the work required to stretch. What is the formula for work? Which is from 0 to half, isn't it? 0 to half. No, it's here. Find the work required to stretch the spring from its natural length to length of 6 meter. Actually, now we have to stretch the spring from 4 meter to 6 meter. This is the length, newly stretched length 6 meter, isn't it? So 0 to 2, 2 meters more you are stretching. F of x dx. And f of x for spring problem, f of x is k times x. Integral 0 to 2k times x dx. And k is known, 12. Keep the 12 outside. Integrate x, it is x square over 2. 0 to 2. So when you solve this one, you will get 4 divided by 2, 2 into 12, 24 joule. 24 joule is the answer for first problem. So find k by using the information given. Use the k for the second term. The same way you can try this problem, problem number 7. What is it? Let's try. How much work is required to stretch the spring 0.8 meter beyond its natural length? We don't know what is its natural length. Okay, you have to stretch beyond its natural length 0.8. 0 to 0.8 you are stretch. F of x dx. This is the formula for work done. Obviously this is 0 to 0.8 k times x dx. F of x is equal to k times x by Hooke's law, isn't it? Question is, what is k? That should be found by using the first information. 100 F is 100 Newton and the distance x is 0.2 meter, stretched 0.2 meter beyond its natural length. So 100 is equal to k times 0.2. Therefore k is 100 divided by 0.2. It is 500. So k is 500. That is to be used in this equation. So let's integrate now. Therefore w is integral 0 to 0.8 k is 500 x dx. When you take 500 out, when you integrate x square over 2, 0.08. Now use calculator. 500 divided by 2 is 250. X square is 0.8 whole square minus 0 square. Use calculator, you will get it. This is 160 joule because the Newton and meter involved. That's the end of this problem. And the last problem of this chapter is this topic. Yes. Assume that 10 foot-pound of work is required. Work is given 10 foot-pound to stretch a spring 1 foot beyond its natural length. 1 foot. So you are given that the formula for W is 0 to 1 foot beyond its natural length. 1 foot, isn't it? What is this spring constant? Question is, what is k? So this is k times x dx. And W is 10. When you integrate x, it will be x square over 2 from 0 to 1. So this is k over 2 here, which is equal to 10. This gives k is equal to 20. Work is pound by foot. So this is k is pound per foot. That's the end. That's the end of this chapter. Thank you. And we'll see the next chapter, hyperbolic function, the next video. Thank you very much.